All right, so good morning, everyone. So I'm Alexandre Le Boité. I'm a CNRS researcher at Laboratoire MPQ in Paris. And I'm going to talk about quantum optical system with non-trivial topological properties, and where it's really the non-linearity and spontaneous symmetry breaking that play the key role. But first, I would like to thank the organizers, both for the very stimulating scientific program, but also for all the logistical efforts. So it's very much appreciated. And speaking of acknowledgement, I would like to say that this work is a collaboration with people in Rome. So at University La Sapienza, so Simone Felicetti and Valentina Brosco, and Alessandro Coppo, who is a postdoc in the group, and he is the one who did most of the calculations. So this collaboration also reflects the fact that, in a way, this project comes from two lines of research. So the first one is the idea of phase transition in a finite component quantum optical system that have been studied in the last few years, and also all the much larger questions of the effect of nonlinearities in a bosonic topological system. So first, I would like to say a few words of background on these two topics to see how they come together quite nicely. So in terms of phase transition in finite component systems, one configuration that was studied first, I think, was the case of dissipative phase transition. And to illustrate that, I will take the example of a single Kerr resonator with a 2-photon pump. So really, like I write here the Hamiltonian of this is a driven system in a rotating frame with on an oscillator with nonlinear time plus a 2-photon pump, and in a dissipative setup, it was considered also 2-photon and single photon loss, and this was a theoretical. This was a theoretical study that was done at MPQ. Some time ago. I think it was actually presented also in Cargèse back in the days. And so they saw in the system providing a correct scaling of the parameters, various type of phase transition between a low population of photons to a high population of photons. And so the reason why I'm talking about this particular example is because first, this will give me the building blocks of my topological system that I will show later, but also because it has recently been observed in experiments in the group of Pasquale Scalino and with superconducting circuits. So this also is an inspiration to go further in this direction. In terms of phase transition, there was also some studies of this type of transition in a closed system. So in the case of dissipative phase transition, it was induced by external driving, but it can happen also without in a closed system, provided that one can define an effective thermodynamical limit in the system, and one varies some coupling to some critical values. So we have worked on this with Simone, and what we have shown that in the case of two components, if you ramp up the coupling between them, you can end up with a phase transition to phase with a parity breaking and twofold degeneracy. And this property arises in quite a large class of systems because they are rooted in the, let's say, parity symmetry of the light matter dipolar interaction. So that's what we call them universal. And as an example of this kind of situation, again, we can consider coupled resonators with this type of interaction. So here in the context of quantum optics, we would say that we have both rotating and counter-rotating terms in this case. And the thermodynamical limit is given by a scaling on the nonlinearity. So what is interesting in this situation is that the nonlinearity can be vanishingly small, but it plays an important role to stabilize the phase above this critical point. So the reason I'm also talking about phase transition in closed system is because afterwards I will neglect dissipation for some time and be inspired more by results in the closed system, and mention dissipation briefly at the end. But before really going, I will also to mention, of course, that nonlinear effects in topological bosonic system is a very active field, and there have been a lot of work on how to measure or calculate nonlinear effect in systems that have an underlying topological structure. I think we will hear more about this later in the conference. But what I would like also to mention is that you have also another direction, which here you have two examples of recent or less recent papers, where basically you induce some kind of emergent topological structure by some external drive, and you look at excitations. So here there's a chiral drive that breaks the time reversal symmetry. But so in what I'm going to show is share some ideas with this philosophy. And one specific features of the model is that in the model I'm going to show, there is a transition from an atomic limit of decoupled oscillator to topological phase. So it's really the whole band structure, let's say, that is emergent in this case. So that's bring me to the core of my subject. So to probe this idea of interplay between this phase transition and the single site level and the emergent topological phenomena, we chose to explore first the 1D chain of these parametric oscillators. So we chose the SSH configuration, which has known topological properties. So the idea is we take a chain of oscillators, but you have actually two sublattices due to the fact that you have two kinds of coupling. So here coupling between within a single cell, and here epsilon 2 is the coupling between the cells. So in my particular case, what at the local site level, so we consider these nonlinear oscillators with these two photon driving, and then the coupling terms are actually cross-Kerr nonlinearity. So it's not a quadratic Hamiltonian, it's a quartic Hamiltonian that couples the two different cells with this structure. And so the whole Hamiltonian is given by the sum of the two. So what we want to consider is the weak nonlinearity regime, and the physics in this regime will be governed by the ratio between these different nonlinearities. And what we expect is, because we have this driving, we expect some, so there is a transition for when this two photon pumping is larger than omega, and in the thermodynamical limit we will we'll enter symmetry breaking phase, and this is the phase that I'm going to be interested in, because this is where the non-trivial structure can emerge. So a bit more about the relevant parameters that will govern the phenomenology of the system. So one important parameter will be the ratio between the cross-Kerr interaction that will couple the different size of the local Kerr, and this will tell you if you can hybridize these two sublattices and really have the band structure or not. And of course, there is the topological features that are quantified by the imbalance between the two type of couplings, intracell and intercell coupling. So this is similar to the standard SSH model, except that here it's really nonlinear couplings instead of just tunneling rates. And since I'm going to be interested in really the phase above threshold with a lot of photons, there is also this number of photons that will scale with this parameter g squared, and it will give you like the general energy scale, but in the phase of like symmetry broken phase, where I expect that lambda is much larger than omega. The two key parameters are going to be these two ones, and this is where this non-trivial topological structure is present. So the fact that I'm considering this is also because I want to be sure that I have a lot of photons and that I can start to explore the system with the semi-classical approximation and plus add on top of that Gaussian fluctuations. So just to give you an idea of, to illustrate, let's say, this idea a bit more precisely, I want to show the picture of what you obtain if you take just a single cell of two resonators. So this is the Husimi function of the ground state. So basically the decomposition of the ground state into coherent states. And since I have two oscillators and each oscillator has two complex variables, it should be a four-dimensional picture, but in fact, the real part of these parameters is zero in this particular case. So with these two, with this plot, there is one parameter for one oscillator and the other one for the other oscillator. So you have the two oscillator system here, and what you can see is that you see the phase transition. So below threshold, you have just a ground state that is the vacuum, and above threshold, you have a state with a non-zero population of photons. And the picture here, I mean, the type of state you get will depend on this mu parameter. And in particular, it's only when mu is smaller than 1, then this state that will become the symmetry broken phase are hybridized between, so let's say populated both on the two oscillators, while here, when mu is larger than 1, only one, in these individual lobes, only one oscillator is populated. So what is going to be the most interesting part for us is really selecting one of the states that have both population of photon in both sublattices, and this is where interesting things will happen. Okay, yeah, I will also mention some work by people in Constance and Trento on this dissipative case of these two oscillators. Yes? Yeah, so so here the phase is defined by the drive basically.
Yes, but it will be the same for
yeah.
every share or commutator flux.
Yeah.
Okay.
So now, yeah.
What's epsilon L? That is the
epsilon L is the local Kerr non-linearity of my oscillators. So yeah, something I can mention maybe is that the reason why, so here basically this happened when the local Kerr dominates, so it's not energetically favorable to populate both sublattices, but just one, because the local interaction costs too much energy, while when mu is smaller than 1, it is favorable to delocalize to hybridize the two modes, to let's say to populate the two modes.
So just one quick thing.
Yeah.
You mentioned symmetry breaking. What probably missed it?
No, I mean, so the symmetry actually you see it here. So there is a general parity symmetry in this problem, is that because of the form of the interaction and this two-photon drive, what is conserved is so you can change, like in a semi-classical solution, you see here you can change alpha by minus alpha and beta by minus beta. That doesn't change. So you see, when you have two resonators, you have a four-fold degeneracy. And if we have an extended system with a lot of photons, etc., I expect a symmetry breaking of this degeneracy and this parity symmetry at some point. And I guess in the driven dissipative case, I would maybe expect a metastable state that has the same properties.
And so about that, actually, when you're talking about the invariance, is it invariance under the application of this symmetry on all n at once, or invariance?
No, you can change locally. So yeah, yeah, yeah. Yeah, because basically what you have things locally, and the coupling terms are also, each coupling terms is also invariant because it's a care. So yeah. Okay, so this is this is a numerical calculation at the semi-classical level for 25 sites in this regime, and this is the basis for then looking at quantum fluctuation on top of this semi-classical solution. So basically a coherent state on each of the sites, and then I can follow the Bogoliubov procedure to treat that at the Gaussian level, and this is where things get interesting. So basically what is happening is that if you expand your solution in this form, you get a quadratic Hamiltonian. And this quadratic Hamiltonian is very generic. It has all kinds of terms, but there are two things that are important, is that all these, the terms appearing, especially these effective tunneling terms that you get between the different sites and intercells, are now depending on the parameter alpha n and beta n. So depending on on the steady state, you will get these this effective Hamiltonian for the excitations, and of course you can, since it's quadratic, you can diagonalize it with the Bogoliubov transformation, which takes this form where you have two bands because of the two sublattices, like in the normal SSH model, and then you can find the spectrum. And here, basically, we have all ingredients to try to see whether or not you have some topological properties in this case. So from the Bogoliubov diagonalization, we can see if there are localized states in the finite size, or try to compute topological invariance with periodic boundary conditions. Yeah, so, sorry? Yeah, so here, yeah, no, so, yeah, it's the emission conjugate, but it was cut at some point. It was, yeah. So yeah. So this is the full Hamiltonian plus Hermitian conjugate of this part that is missing.
So between two cells, you have both just excitation property and squeezing terms.
Yeah. So that's why I said, like, it's a generic quadratic Hamiltonian, but it will inherit properties from the SSH structure, and at the same time, it's entirely generated by this phase transition to high number of photons. So then, of course, as I said, once you have that, we can ask the question of the bulk boundary correspondence. And so the first step is to calculate topological invariant with the periodic boundary conditions. So it's a 1D system, so it's the Zach phase, and we find the same result as in the SSH chain. That is, when delta is smaller, is larger than 0, we have a non-zero Zach phase, while it's trivial, topologically trivial in the delta smaller than 0 regime. But then the question arises of what is happening with open boundary condition. And then here, so if I plot the energy spectrum as a function of delta, so this is not a Brillouin zone, but really the spectrum for different values of beta. In green is where I would expect these topological edge states to be located. But the problem is that this bulk boundary correspondence cannot work in the usual way, in the sense that my steady so the tight binding Hamiltonian on which I'm computing the topological invariant actually depends on the boundary condition itself. So I lose this boundary condition, and actually these states are not localized states, so they're not. So if you do this like that, you end up, you lose the topological properties because of this specific feature of the system. But we can restore this by actually tuning, adding a small driving on the edge of the chain, so to restore, in the sense, or let's say attenuate the effect of the boundary condition. And I can show you example of calculation in this case, is where now we recover some localized states that are between the two bands. So these are actually the topological protected localized states in green here. And there's also some states that in the topologically trivial part of this diagram, but we can relate these two localization by different mechanisms. So this, especially if you take the extreme part of this, you can see that this comes from the localization induced by the disorder introduced with that, and this will survive up to a certain value of delta, and this is not related to any topological feature, while here it will remain localized within the full topological region. And you can see if you compute the localization length of these localized states, you see that they follow different behavior, and this one in particular is the one you would expect from SSH behavior. So to conclude, I would say on this part is that I can restore this bulk boundary correspondence by adding some perturbation, small modification of the driving to attenuate this effect of boundary condition in my problem. So until now, I talked only about closed system, and in a way, I know that in experiments we have to take into account dissipation and driving dissipation, but there is an hypothesis that says that some of the properties of the ground state and of this excitation are going to be transferred to a steady state in a dissipative case. So this is true at the semi-classical level if you look at the equations, but to explore this further, of course, the next step is to include dissipation within a Lindblad master equation formalism. So here I write it only with single photon losses, but in principle one can also include two photon losses or pure dephasing. And the plan also is to treat that using a phase-space approach, because the parameters that we use are the fact that we have weak non-linearities make this approach relevant in a sense. So this phase-space approach stems from the fact that we can represent the density matrix of the quantum system in such a way that when I compute the observables, like the moments of my bosonic modes, I can compute them using some function. Here I denoted P of the coordinates in phase space alpha n, beta n for each mode. So this is, let's say, mapping to a phase space, and this mapping allows to map the Lindblad quantum master equation with operators to some kind of Fokker-Planck equation when you are, when things go well, let's say that it can be mapped to a Fokker-Planck equation in the relevant regime, and then the advantage is that you can simulate it with stochastic Langevin equation and parallelize it on multiple CPUs. And so when you are able to do this mapping efficiently, you can also scale your system in size, because this is much cheaper to simulate. And this is ongoing work, and I'm working on this with my colleague Giuliano Rosso and our student Bosco Dalini at MPQ. With this, I will conclude. So in summary, I've presented some theoretical results on a system where if you have a cross-Kerr SSH model with only nonlinear couplings and this mechanism of phase symmetry breaking, you can really go into a phase where there is non-trivial topology induced by interaction, and which gives rise to a non-trivial bulk boundary correspondence where you can restore this topological eighth stage with non-uniform small correction. And of course, the next step is to extend this to dissipative systems to be more realistic when compared to experiment, to see if this is robust and if in what condition. And also we could then also extend to potentially two-dimensional systems, for example. With that, thank you for your attention.